A warm welcome to all the students. In this lecture, we are going to study minimization of DFA. Now, what do you understand by minimization and why it is required? As we have already discussed, for every DFA, okay, that DFA represents one unique language. So, if you have designed a DFA for one particular language, that DFA will not be able to recognize any other language. Okay, so the concept that we have seen so far, okay, it just tells you that if there is one regular language, then there is one unique DFA. Okay, now just see the relation. Now DFA identifies one unique regular language. The same DFA will not be able to identify any other language. So every DFA identifies one unique regular language. But the reverse relation, that is every regular language does not have a unique DFA. Okay, it may have more than one DFA. So although every DFA recognizes exactly one unique regular language, every regular language may not have one unique DFA. It may have more than one DFAs, equivalent DFAs. Okay, now the problem occurs where many a times the DFAs that we have, they are so complex. There are so many number of states in the DFA, there are so many transitions in such DFA, okay, the realistic DFAs that we have, okay, so they look complicated. Now, as a result, as the DFA is complicated, as you know, it is a tool used to recognize certain things. It is a tool used to which is used in different processes, maybe in compilers and so on. Okay, as the complexity of DFA itself increases, definitely the processing power will, the processing complexity will also increase, right? So in this concept here, minimization of DFA, what we are trying to do is, if we have a very complex DFA that is given to us, we are trying to convert that complex DFA into a simplified DFA which is equivalent, which will do the same task what that complex DFA does. So minimization refers to converting a very complex DFA, realistic DFA, into a simplified version which is an equivalent of the original DFA. So minimization of DFA refers to minimizing or simplifying that complex DFA into a simpler one without changing the meaning of the original DFA. Now, before we go through this concept of minimization of DFA, there is a procedure to do it. We have to go through a few preliminaries. Okay. Now, what are the preliminaries? The first concept that we are going to see is called as equivalent states. Two states P and Q in an automata, they are said to be equivalent if and only if extended transition function for state P when a string W is read, and extended transition function for state Q when the same string W is read, okay, results in both accepting states or both rejecting states. Let me simplify this. Now, what is the meaning of extended transition function? Extended transition function, which is written at del star, it just tells you, okay, if we are in a particular state P, and when a particular string W is given as input to this extended transition function just tells you, after reading this entire string, which state the automata will be in. That's the meaning of extended transition function. So this means starting with state P, on the reading string W, okay, the extended transition function will take you to a particular state. Similarly, from state Q also, on reading the same input string W, the extended transition function will take you to one particular state. Now, if both these states, the resultant states, if both of them are accepting states or if both of them are rejecting states, then we can say that P is equivalent to Q. Let us see this with an example. Now we have a DFA that is given to us here. Okay, let's see an example here. Okay, in the above example, state P, Q, R, S and T. Okay, if you can see state P, Q, R, S and T, they are all non-final states or non-accepting states, whereas there is only one final or accepting state, that is U in the diagram. Okay, now we will say the state Q and R are equivalent to each other. Okay, looking at the diagram, okay, we say that state Q and state R are equivalent to each other. So I can say the state Q and the state R, both of them, they are equivalent to each other. Why? Because extended transition function from state Q on reading 0, 1. Now from state Q, when the entire string 0, 1 is read, where it takes you? It takes you to a state called as U. Okay, so from Q, when 0 is read and then subsequently when 1 is read, Q is going to take you to a state called as U. Similarly, extended transition function from the state R on reading string 0, 1 also takes you to a particular state called as U. So from state R on reading 0 and then on reading 1, it again takes you to the same to a particular state called as U. It may be same state, it may not be same state, but you observe that whichever state both of them both this particular extended transition takes you, both these states, they are final state. So U is a final state. Okay, this U is also a final state. So according to the definition, I can say now that Q and R, state Q and state R, they are equivalent because, okay, on the reading a particular string, say 0, 1, okay, they reach in a state such that both these states where they reach, either both of them are final states or both of them are non-final states. In my example here, both of them are final states. Okay, so let's go further. So in general, okay, in general, what is the meaning of equivalent states? If extended transition function from state 1 on reading one particular input takes you to an accepting state, and extended transition function from another state in the same DFA on reading the same input as the first one also takes you to a accepting state. Now this accepting state and this accepting state may not be the same state. There may be, I told you, in a DFA there might be more than one final states. So let's say this extended transition function here takes you to a different final state of that DFA, and this extended transition function takes you to a different final state of the same DFA. So let's say these two are different final states. Since both of them are final states, we can say that state 1 and state 2 are equivalent. Okay, so in simple words, in plain simple words, from a particular state of DFA on reading a particular input, if it is taking you to one of the accepting states, then from another state on reading the same input, that also takes you to an accepting state. Since state 1 and state 2 on reading the same input takes you to accepting states of DFA, I can say that state 1 and state 2 are equivalent to each other. This result may be also stated this way. Suppose now, same thing, extended transition function, state 1 on reading input 1, the full input 1, finally takes you to one non-final state. It may not be, these two may not be the same states. So state 1 on reading a particular input, say input 1, takes you to a non-final state, and state 2 on reading the same input as what was read by state 1, okay, also takes you to one of the non-final states. Notice that both these non-final states may not be the same state. They may be different states in the same automata, different non-final states in the automata. But since both the states, state 1 and state 2, on reading the same input, both of them take you to non-final states, maybe the same state or maybe different non-final states. Since both of them take you to the non-final states, then also I can say that state 1 and state 2 are equivalent. So in general, two states P and Q, they are called as equivalent to each other if on reading the same input, either both of them take you to the accepting states only, or both of them take you to the rejecting states only, or non-final states only. Only then the two states are equivalent. Okay, now again when we consider this diagram, okay, let's take an example now. From state Q, okay, on reading say string 0, from state Q on reading string 0, it takes you to S, right? What is S now? S, is it the final state? No, S is a non-final state. Now from state R on reading 0, it takes you to T. From state R on reading 0, which is the same string that is read by previous extended transition function, it takes you to T. So that means from state Q in the diagram on reading 0, the automata makes transition to S, which is a non-final state. Similarly, from state R on reading the same input 0, from R on reading the same input 0, the automata takes you or makes a transition to T, which is also a non-final state. Notice that this S and this T, both of them are non-final state, but they are not the same state. They are different states of the automata. But since both of them, S and T, both of them are non-final states, I can easily say that Q and R are equivalent to each other. Okay, so in general, okay, two states are called as equivalent if on reading the same input, either both of them takes you to final states or both of them take you to the non-final state. So that's meaning of equivalent states. Okay, equivalence of two states. Okay, now while solving the problem, you will see that equivalence can be also denoted this way. Now for example, Q and R, both of them are non-final states, so I can say both are equivalent. Similarly, S and T, okay, both are non-final states, so they are equivalent. That way also the result can be said. Now we'll see the next definition, that is called a distinguishable state. Okay, now in the previous example, in the previous terminology that we saw, we said that two states are said to be equivalent to each other if on reading the same input symbol, either both of them take you to the non-final states or both of them take you to the final state. Then they are called as equivalent. Now exactly opposite definition of equivalent is called as distinguishable. What if this state on reading an input takes you to a final state, and this state on reading the same input takes you to a non-final state? What if both of them are not final or both of them are not non-final states? What if one of these states on reading the same input, what if one of these states is a non-final state and other one is final state? Then Q and R, they are called as distinguishable states, and that is the definition that we are going to see now. So what is distinguishable state? Two states P and Q are said to be distinguishable when there exists a string A, a common string, when there exists a common string S belonging to sigma star, such that either transition from state P on reading that whole string S results in an accepting state, and transition from state Q on reading the same input symbol S results you into non-accepting state. That means one gives you accepting state, other one gives you a non-accepting state, or vice versa. If any one of these resultant states happens to be accepting state and the other one being non-accepting state, then P and Q together, they are both called as distinguishable to each other. Okay, so now again looking at this same DFA diagram, in the figure, as you can see, I can say that state P and S are distinguishable. You see state P and you see state S. I say that both of them are distinguishable with respect to string 1, because if you see, if you consider the extended transition function, from state 1 on reading the whole string 1, it takes you to Q. So from P on reading 1, it takes you to Q. What is Q? Is it a final state or non-final state? It's a non-final state. So Q is a non-final state. Now from state S, on reading the same input symbol 1, from state S on reading the same input symbol 1, it takes you to U. And what is U? U happens to be a final state. So the first one results you into a non-final state, the second one results into a final or accepting state. So from state P, on reading a particular input, it takes you to a non-final state. From state S, reading the same input symbol takes you to a final state. Since one is final, other is non-final, I can now say with respect to this string 1, okay, state P and state S are distinguishable to each other. Okay. Now minimization of DFA, it represents a unique basically any DFA, okay, it represents a unique regular language. Okay, always remember, any DFA represents a unique regular language. However, vice versa is not true. That means for every regular language you cannot say that there is a unique DFA. Student may draw different DFAs which may be equivalent, okay, for a particular language, but once a DFA is drawn, that DFA will represent only one language, and it cannot DFA cannot represent multiple languages. For whichever language it is drawn, DFA will represent only that language and not any other language. So this you need to find out, you need to keep in mind. So each regular language can be represented with more than one DFA. So now what happens is, when this happens, okay, student may tend to draw DFAs in different ways. A particular student may draw a very complicated, a complex DFA, and another student may draw simple DFA. So many a times DFA may look very complicated, very complex, because student may just go on adding number of states, number of transitions without changing the meaning. Okay, so when such complex DFAs are used in calculation, especially in compilers and all, okay, since the complexity of DFA is basically a graph. So since the graph is very complex, okay, the complexity of the problem increases. So minimization refers to, it's a technique that converts, okay, a very complicated DFA to a very simple DFA. Now next we are going to see procedure of minimization of DFA. Okay, this algorithm is also called as a table filling algorithm. Okay, procedure is very simple. So today we are going to see the procedure, and then in the next, because the problem is a very complicated problem, in the next lecture we are going to solve a problem on this, right? Now what's the procedure of minimization of DFA? Now, if there are n states in DFA, the algorithm guides to build a n-1 by n-1 table. The procedure of minimization of DFA here, it is called as table filling procedure. So basically the algorithm here allows you to create a table, and we are going to, as the algorithm continues, we will be marking cells of this table with X. Okay, we shall see that further. But very first thing you should note that if in the DFA, suppose there are 5 states, okay, then if n is 5, that means there are 5 states in DFA, then the table that we are going to build will be 4 cross 4, 4 by 4, n-1 by n-1. Now each column is named by the name of the states, starting with the first state and excluding the last state. Now each column in this particular in the particular table, each column is named by name of the states, starting with the first state and excluding the last state. Now whenever I say last state, it does not mean the final or the accepting state. You go chronologically, okay, or alphabetically, you go through the name of the states. Whichever state chronologically happens to be the last state, that will be excluded, and all other states will be included. That's called as chronological order. So each column is named by the name of the state, starting with the first state and excluding the last state in chronological order. Each row is named by the name of the state, starting with the second state, excluding the first state in the chronological order. And each row is named by the name of the state, starting with the second state and excluding the first state in the chronological order. Okay, so This is a third point. And fourth one, duplicate cells, for example a comma a, b comma b, c comma c, these are the duplicate cells which are eliminated. Now just to give you the overview of what exactly I've said here, how to build a table, let's take an example. Let me take the same DFA that we had taken here. Okay, so for this DFA, okay, let us see how I can draw a table. I will be drawing the table here. Okay, first of all, when you count how many states are there in the DFA, so basically DFA here P, Q, S, U, okay, T and R, how many states are there? 1 2 3 4 5 6 states are there. So in my example here, n happens to be 6, so the table will be 5 by 5. That means there will be 5 rows and 5 columns, right? So that's the meaning of the first sentence that we saw. Okay, what was the first sentence? It simply said that if there are n states in DFA, then the algorithm guides to build a n-1 cross n-1 table. Now the second and third point here says, now how should we name the columns? Each column is named by the name of the states, starting with the first state, excluding the last state. So in each column, in simple words, in each column, okay, starting with the first state alphabetically or chronologically, you should go on naming them, and you should exclude the last state in the column. Whereas in the rows, okay, in the rows, you should start with the second state and excluding the second state, excluding the first one, and consider the last state. So let's draw a table for this example here. Okay, so there will be 5 rows and 5 columns. Simple. Now how will be the rows and how will be the columns? Okay, now these are called as columns. Okay, let's see each column. In each column, it is told to you that each column will be such that it will start with the first state excluding the last state. Okay, what is the first state in alphabetical order here? So P will be the first state, next Q, next R, S, and T, and the columns will be such that it will start with the first state alphabetically and it will exclude the last state. So U here is the last state and it is also a final state. But even if U was not a final state, okay, suppose S was the final state and U was the alphabetically last state, then we would have excluded U and not the final state. Whichever alphabetically or chronological is the start state, now that you have to skip in the column this. So I will be not writing U because U is the last state. I exclude that. So columns will be such that starting with the first state, okay, go on naming and exclude the last state. Now how will be the rows? Okay, rows will be such that you should start with the second state excluding the first. So what is second state? Second state is Q, okay, R, S, T and U. Okay, so now when you go with this, okay, you are going to get a table kind of. Okay, so you will have Q, R, S, T, and this is for U. So if you see this cell here, it is P comma Q. Okay, if you see this cell here, it is P comma Q cell. If you see this cell here, it will be P comma R cell. If you see this cell here, it is P comma S cell. This cell over here is P comma T cell, and the last cell here is called as P comma U cell. Fine. So this is how the rows and columns will be built. But the next point here is very important. It says, okay, the next point here it says, so we have just constructed, you know, columns and rows. Next point here says duplicate cells are eliminated. Cells such that a comma a, b comma b, c comma c, d comma d, these cells are eliminated. So now in this diagram, okay, if you happen to see the next state here, the next cell here, it will be q comma q. If you see the next cell here, it will be q comma q. So that cell has to be eliminated. That means we are not going to draw that cell. Okay, we are going to exclude that cell. Okay, and as a result, that cell will be skipped from the table, and we will draw the next cell, that is all other cells. So this cell here will be r comma q. Then the next cell will be s comma q. Then the next cell will be t comma q, and the last cell will be u comma q. But this cell here happens to be q comma q, and this is a duplicate cell, so that has to be removed. So I will not be drawing that cell. That's the meaning of it. Now similarly, when you consider this cell here, it is r comma r, so such cell also has to be removed. So I will not be drawing that cell, and I will be drawing all other cells in the table. So the cell over here, this will be s comma r, the cell over here will be t comma r, the cell over here will be u comma r. Similarly, this particular cell here would be s comma s, so that cell also I will be skipping. I will not be drawing that cell. So this cell over here will be t comma s, this cell over here will be u comma s, and finally here also this cell here will be t comma t, so I will be ignoring that. I will not be drawing that, eliminating that, and the last cell that I obtain is u comma t. So this is that table that we are going to get. It is you will always get this kind of table, like, you know, ladder. Okay, so this is how the table is built, and now the algorithm will proceed, and every time it does, okay, based on the calculations in the algorithm, certain states will be marked with x, okay, certain states will be marked with x, and so on, and the algorithm will continue. As we continue, more markings will be done, more markings will be done. Now how these markings will be done, that is there is another procedure for that, which we are going to see. Fine, but at least drawing the table is understood. So again I'm telling you, in the table, if there are 6 states like here, the table will be 5 by 5. So you will have 5 elements in the column, 5 elements in the rows. Now when you consider the column, these are columns, okay, vertical ones are called as the columns. Numbering will start from the first state, second state, third state, and so on, and it will exclude the last state. Okay, what is last state? U over here. Last state does not mean the final state. Final state may be any of these states. Last with respect to the chronological or alphabetical order, so that state will be removed in the column. Now these are called as rows. The horizontal ones, they are called as rows. So row numbering will start excluding the first state. P is excluded. Starting with the second state, we will go on numbering till the last state, and then the cells, like, you know, duplicate cells, for example p comma p, q comma q, and these kind of duplicate cells, they will be eliminated. So you are going to skip drawing them, right? So as a result, the table that you are going to obtain is like this. Okay, so we shall proceed with the procedure of minimization. Next, the cells are marked or filled with X as soon as the two states represented by it are decided to be distinguishable. Okay, so when marking will happen? Marking will happen, okay, marking will happen, this marking which I have done, see here X, 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 randomly I have done without logic, but when can you mark X in a cell? So if it is found that state T and state R, if these two states T and R, if they are distinguishable, if it is found that both of them R and T they are distinguishable, then you will be able to mark X here. Similarly, you can mark X here if it is found that state S and state P, they are found to be distinguishable, then you are going to mark X here. Similarly, if R and Q, they are found to be distinguishable, then X will be marked here, and so on. So basically, the cells will be marked with X. The cells will be marked with X as soon as the two states represented by it are decided to be distinguishable. Now, how distinguishability is determined? For that, there is a small procedure, okay, and that is this procedure. The following procedure is used, okay. Now, if state P is an accepting state, suppose P is an accepting state and Q is a non-accepting state, then the pair of states P, Q is a distinguishable state. The cell P, Q is marked with symbol X. So as a base step in the same example here, looking at this diagram, now just see P, Q, R, S and T, they are all non-final states and only U is a final state. Okay, P, Q, R, S, T, they are all non-final states, but only U is final state. So I can say the state, every state is distinguishable with respect to U. Okay, so now let's see. Now state Q and state P, let's check for this cell. Okay, now state Q, Q is a non-final state, P is also a non-final state. As a result, they are not distinguishable with each other, so I am not going to mark. Okay, I am going to mark only where there is U is a final state in the diagram, whereas state P is a non-final. So one is final, one is non-final, so I can say U and P are distinguishable to each other, so I will be marking X here. Okay, so I will be marking this cell with X. Similarly, again U, so in simple words, state U is distinguishable with respect to every other state, right? So you will see that U, Q will be also marked with X, because state U and state Q are distinguishable to each other. One is final, one is non-final. Similarly, state U and state R will be marked with X, because one is final, one is non-final. Then state S and U will be marked. Why? Because one is final, one is non-final. And similarly, U and T will be marked. One is final, one is non-final. So you will initially, as a base step, mark all those cells where one state happens to be a final state and the other state happens to be the non-final state. In the last cell here, in the last tuple here, you will see that every state is distinguishable with U, because U is a final state, whereas every other state is non-final state, so X's will be marked here. So this is a base step of the algorithm. Okay, let's proceed. Okay, so this was the base step. So cell P, Q is marked with X. We have done it already. Now step 2 is a recursive step. Now given two distinguishable states R and S, suppose we already know that R and S are two distinguishable states. Okay, and if P and Q are some states such that for some input symbol A, for the same input symbol A, if transition from state P on reading A gives you R, transition from state Q on reading the same input A gives you S. Okay, so we may conclude that P and Q are also distinguishable. So in simple word, what it means, just see, suppose we know that state R and state S, they are distinguishable. Suppose we know that state R and state S, they are already distinguishable. We have found in base step, suppose. Now we have transitions of this type. From one particular state P on reading A, it is taking you to R. From another particular state Q on reading the same input A, it is taking you to S. So since P and Q, which are some random states, on reading the same input, they are taking you to two particular states, and R and S are already found known to be distinguishable. Since P and Q on reading the same inputs are taking you to a pair of states which are distinguishable, I can now say further that P and Q is also distinguishable. That's why the pair of states P and Q is also distinguishable. Thus, p comma q will be also marked with x. Okay, so this is a recursive step of the algorithm, right? Now while solving problem we will see this more. So this is the second recursive step of the algorithm. And finally, okay, once this is done, what will happen is, in the table, as you go on solving, okay, as you go on solving, you will find out that in the table all the states will be marked with x. Okay, all the states will be marked with x, and there will be some states that remain to be marked. For example, say this state is not marked, okay, or say this state remains, it is not marked. That means it is found that r and q are not distinguishable. Example, suppose this state is also not marked, so this state is also not marked at the end. So which simply means that state r and state q, okay, they are equivalent. Okay, why? Because at the end of this procedure, at the end of solving, okay, we find that it is only this cell which we were not able to mark with x. That means r and q are not found to be distinguishable. So we have already seen the terminology. Opposite of distinguishable is equivalent. So since r and q were left to be marked, it means state r and q are equivalent. Similarly, here for this cell, okay, suppose t and r were left to be marked. That means we were not able to mark this. It simply means t and r are also equivalent, and so on. So this way we will find out which are the equivalent states. And then finally, the minimized DFA. Okay, what will happen in minimized DFA? In the original DFA, now since, suppose example, q and r, suppose they are now found to be equivalent. So in the original diagram, q was a separate state shown, r was a separate state shown. But now since we have found out that r and q are actually equivalent, okay, what in the resultant DFA we will do is, we will club these two, r and q, together as one state. Okay, and so whichever states are found to be equivalent, those states will be clubbed together as one state, and we will be drawing the DFA. So this is what we are going to do while solving the problem. Okay.